Hi everyone, I'm meteorologist Gary Woodall, and welcome to this episode of the Mid-South Weather Musings. In this episode, we are going to get into the science of thunderstorms and talk about a couple of important ingredients that we need in the atmosphere to get thunderstorms to form. And those ingredients are moisture and instability. So let's take a closer look at these two secrets of the storms. Moisture, humidity in the atmosphere is an important ingredient for thunderstorms. The moisture, the humidity that's in the atmosphere actually goes on to form the clouds and the rain and the hail that we associate with thunderstorms. Now, most of our moisture for thunderstorms comes from the Gulf of Mexico. Southerly winds will bring that warm, moist air up into the area, and this is usually low-level moisture and about the lowest mile or so of the atmosphere. We also can sometimes get mid-level or upper-level moisture, maybe 3 to 6 miles up above the ground. This mid and upper-level moisture often comes into the area from the Pacific Ocean. Now, when it comes to heavy rainfall, storms that might produce very heavy rain, we'll often have both this low-level moisture from the Gulf and the mid and upper level moisture from the Pacific. That really sets the stage for very heavy rainfall, possibly from thunderstorms that form. When we're talking about severe thunderstorms, the low level moisture is primarily what is focused on. This is the primary and necessary ingredient for severe storms, this low level moisture in the lowest mile or so of the atmosphere. Another important ingredient for thunderstorms is instability in the atmosphere. Now, what in the world do we mean by instability? Well, instability is basically how much energy is there in the atmosphere. And to investigate instability, we start out with a parcel of air, a blob of air that's maybe about the size of the room that you're in, and we theoretically force that air to rise up into the atmosphere. We then will compare the temperature of our blob of air, our parcel that we've lifted, compare that to the nearby environment that our theoretical storm is forming in. If the blob of air, our parcel of air, is warmer, lighter, less dense than the environment, it's going to continue to rise on its own. And when that happens, we say the atmosphere is unstable. Now, on the other hand, if we take our parcel of air, force it to rise, and it becomes cooler, heavier, more dense than its environment, it's going to want to sink back down to where it started. When that happens, we say the atmosphere is stable. So instability, this tendency for our air parcels to want to continue to rise upward on their own, that's one of the necessary ingredients for thunderstorms. Now, in the real atmosphere, we usually find what's called conditional instability, or the atmosphere is conditionally unstable. The condition is whether or not our parcel, our blob of air that we're lifting, is saturated or not. Why does that matter? Well, as our air parcel becomes saturated, the water vapor, that humidity, is going to condense, start to form little water droplets, and start to form a cloud. When that happens, when that process happens, a little bit of heat gets released by that condensation into our air parcel. And that is going to allow our air parcel to cool more slowly as it rises up through the atmosphere. So the saturation and this condensation and the forming of the cloud will make it easier for these air parcels as they rise up to stay warmer than the environment and to keep going upward. And that is, again, what we mean by instability or conditional instability and the role that the cloud can actually help play. So on a typical severe weather day, we will have instability in the atmosphere. And typically, we'll find a layer of relatively warm, moist, humid, muggy air, in this air that's been brought up into the area from the Gulf of Mexico, in the lowest mile or so of the atmosphere. Above that, we'll have a layer of relatively cold air, maybe 3 to 6 miles or so up above the ground. So if we can take some of our warm, humid, muggy air down here, give it a little nudge upward, a little push upward, Well, we could start the condensation, start forming a cloud, get that little extra heat released into our parcel, make sure that that parcel stays warmer than its environment, its surroundings, and they can continue upward on their own. On the other hand, we can take some of our relatively cold air up here, give it a little push downward, a little nudge downward. It's going to be colder, heavier than the surroundings, and it may continue to sink on its own. This is what we mean by instability, and this is what helps give rise to the updrafts and the downdrafts, those upward and downward moving air currents inside the thunderstorm. So how do we investigate or calculate or estimate the amount of instability that's in the atmosphere? Well, to do that, first we have to know what the large-scale environment is like. For the current environment, we use weather balloons. So there are about 70 sites across the country that release balloons with instrument packages. Those packages, those instruments will sample the temperature, humidity, pressure, and wind as they go up through the atmosphere. And that will tell us what the current environment would be like. For the forecast environment, we turn to our numerical models, and the models are getting detailed enough now that they can actually give us what the high resolution forecast environment might look like 12 or 24 or 36 hours out into the future, so we can see what the environment might be like on a particular severe weather day. We then take our parcel, our blob of air like we talked about before, lift it, hopefully get it to form a cloud, continue lifting it, and then again compare the temperature of our parcel to the environmental temperature. And we then sum up how much of the environment is our parcel going to be warmer than the environment, so how much buoyant or positive energy is there in the atmosphere. And we also sum up how much negative energy, how much of the environment is our parcel cooler than the environment. So how much inhibition or how much of a cap or a lid is there, in particular on the lower portion of the atmosphere. Now, because these are energies that we're looking at, we do have a couple of energy terms that we look at. CAPE is the convective available potential energy. This is the total positive buoyant energy in the atmosphere. How much energy is there for a storm to work with? And then SIN is the convective inhibition, or how much of a cap or a lid is there on the lower portion of the atmosphere that's going to try to block those parcels from rising and forming a thunderstorm. And since these are both units of energy, they are joules per kilogram of air for those of you that are interested in that kind of thing. Now there are some important layers in the atmosphere that we look at. LCL is called the lifted condensation level. That's where the cloud base starts to form. That's where our parcel becomes saturated, and that's when we're going to start to get that extra heat as the cloud droplets form. Then we would have the SIN. The cap or the lid is usually going to be right on top of that low-level, warm, moist air down close to the ground. So our parcels are going to have to fight their way through this cap, through this lid, to go on and form a thunderstorm. LFC, the level of free convection. That's the level where our parcel breaks through the lid, first becomes warmer than its environment, so it's going to take off on its own from there, develop the thunderstorm updraft, and tap into that CAPE, that buoyant energy that's in this portion of the atmosphere. Now we have different ways that we can calculate or estimate CAPE, different flavors of CAPE, if you will. We can lift a parcel of air from right off of the ground. This is called surface-based CAPE. Shows us what the environment will be like for updrafts that are getting started right off of the ground. We have something called mixed layer CAPE. For mixed layer CAPE, we average the conditions through the lowest, about 3,000 feet or so of the atmosphere, and then lift a theoretical parcel based on these average conditions. Why do we want to do that? Why go through this extra effort? Well, on the afternoon or early evening of a lot of our thunderstorm days, the lower atmosphere gets pretty churned up, kind of mixed up by the daytime heating, by the gusty winds that may be blowing through. So this ML Cape better approximates for us this churned up atmosphere in the lower levels like we see in the late afternoon or early evening. Then there's a third flavor of Cape called Most Unstable Cape, or Mu Cape. With Mu Cape, we actually will look at a number of individual levels through the lowest about 9,000 feet of the atmosphere, find the one of these that is most unstable, and then lift that to do our Cape calculations. So if ML Cape is a big effort, why in the world do we go through all this trouble? Well, sometimes we can have little shallow cold fronts that will move through, little shallow layers of cool, stable air down close to the ground. But we may still have warm and moist air up above there, so may still be able to get thunderstorms forming up above that surface cold front. So if we did the Cape calculations, the surface-based or the ML Cape with that shallow layer of cool air, well, these calculations are going to be all messed up. They're not going to be representative of that warm, moist air that's up above our cold front. Mu Cape can let us find those layers up above our shallow cold front and see just how unstable it is and if we might be able to get those thunderstorms forming up above that shallow cold front. So surface-based, ML Cape, Mu Cape, MU Cape. If you read the Storm Prediction Center's discussions or look at some of the other meteorological discussions, you might see those abbreviations. And again, they're just different ways of evaluating how much instability, how much energy is there in the atmosphere. So there are three ways that we can destabilize the atmosphere. We can heat the lower levels, make that low-level warm air even warmer. And we usually will see that during the course of the day. That's why our prime time for a lot of our severe thunderstorms is during the late afternoon and the early evening hours, when we've had maximum daytime heating, maximum heating of the low levels of the atmosphere. We can cool the upper levels of the atmosphere, and sometimes this will happen as an upper level weather system is moving in. That can bring a little bit cooler air as well. But the most effective way that we can add instability to the atmosphere is to moisten the lower levels, more of that humid Gulf air coming up into the area. And a lot of times that's going to be a critical factor. How much of the warm, moist air is going to come up from the Gulf and make it up here, be in place when the thunderstorms form. So this is often, it is the most effective way to add instability to the atmosphere, but it oftentimes is one of the trickiest ones to try to predict. So as far as Cape values themselves, if we have Cape values that are roughly above about 250, that seems to be kind of a threshold for any sort of a thunderstorm updraft. If we have Cape values that are above 1,000, that seems to suggest an environment that's favorable for strong updrafts to occur, maybe a more favorable environment for strong or severe thunderstorms to form. Now, as far as the cap strength, the SIN values, they are negative energy, so they have minus signs. If it's weaker than about minus 100 in the morning or weaker than about minus 40 in the afternoon, then the cap may be weak enough that those rising parcels, those updrafts that are trying to form, may be able to break through and go on and form thunderstorms. So how can we track this instability? How can you all see how unstable it might be on a particular day? Well, a great way is using the Storm Prediction Center's website. Go to their website, www.spc.noaa.gov. When the main web page loads, click the Mesoanalysis tab. And you'll then have a map of the country with a bunch of, you'll see subsectors, little rectangles on there. Click the one that is your area of interest, probably one closer to the Mid-South here. And then you'll get a page like this that loads. Then click on the Thermodynamics tab, this one right here. A little drop-down menu will come up, and you'll see all the different flavors of Cape, along with the SIN, the other factors as well. surface-based, ML Cape, MU Cape will all be there. So you click on that and you'll get a map like this. The Cape is shown by the red contours. The SIN areas are shown by the blue shading like we see up in here. So that is a rather detailed introduction to moisture and in particular instability. Again, a couple of important secrets of the thunderstorms, a couple of very important parameters, ingredients that are required for thunderstorms to form. Challenging to observe, more challenging to forecast sometimes. But again, they are important ingredients for thunderstorm formation. And that's going to wrap it up for this episode of the Mid-South Weather Musings. Thank you for watching and viewing the episode this evening. If you like what you saw, please subscribe to us if you're on YouTube and follow us. If you're on Facebook, be sure and like the page as well. And if you have any suggestions, anything else that you'd like to see or know about as far as thunderstorms or weather in general, put it down in the comments section. We'll see if we can work it into a future episode of the Musings. So thank you all so much for watching. Everybody keep safe.